In Module 6, we're going to be introducing the concept of entropy, which is covered in Chapter 7 of your textbook. And we're essentially going to be looking at the second law for a process now. In our previous module, we looked at the second law for a cycle and analyzed how we could understand how far a cycle was from ideal. Now we're going to go into our processes, and we're going to introduce the subject of entropy, and entropy is going to help us deal with the second law quantitatively. So we're going to introduce entropy. And it's going to help us, this entropy is going to help us deal with quantitative analysis of the second law. And we start with something called the Clausius inequality. So later on in this module, we're going to describe what entropy is and how it actually works. But essentially for now, you can think of entropy as the process of going from always going to more order, essentially, or temperature essentially always spreading out, or heat always spreading out between the systems. And we've seen examples of entropy such as the hot cup in a cold room, for example. You know that the heat goes from the hot cup to the cold room and everything sort of becomes balanced. And we'll look at entropy a little bit later and describe it in terms of what is actually happening at the molecular level to try and understand it. So the Clausius inequality is the basis for the definition of entropy. And it was first stated by a German physicist called Clausius, and he was one of the founders of thermodynamics. He also made one of the statements of the second law. And this Clausius inequality says that the closed integral of dq over t is always less than or equal to 0. Okay, so we can write this in words as the cyclic integral of dq over t is less than or equal to 0. And this doesn't really make any sort of sense right now, but he basically found out through this inequality that this inequality was valid for all cycles. So if you do the integral of dq over t, you'll never get higher than 0 for a cycle. So it has to be applied to a cycle, not just one process, okay? It's this integral with a circle is called a cyclic integral or a closed integral, and it's an integration over the whole cycle. So essentially what this integral is giving us is the sum of all the differential amounts of heat. Through a process divided by temperature. And what was found is that when you have a reversible process, the integral of dq over t for a reversible process, so I'll put rev for reversible, is equal to 0. And the integral of dq over t for an irreversible process, and I'll put IRR, is always less than 0. And we can actually do a little bit of an experiment and follow this experiment. So let's look at how we can define entropy. So let's say that we have a system, okay, so a control mass system. We're going to have a control mass system. And this control mass system is going to undergo a reversible process from state 1 to state 2. Okay, so we're going to have, if we draw a PV diagram of our control mass system, we're going to have a reversible process from point 1 to point 2, and we're going to call this process A, for example. Okay, and then in order to complete the cycle, there's another reversible process that goes along path B to get back to the original position. So A and B are both reversible. And if we write the closed integral of dq over t, we have the cyclic integral of dq over t would be equal to 0 because it's reversible, okay? And this would be equal to the integral from 1 to 2 of dq over t along path A plus the integral from 2 to 1, so we just add all the integrals, plus dq over t for path B. And now we have, let's call this equation 1. We have an equation for the system. Now, let's consider another reversible cycle, but now we're going to go along path C to get from 1 to 2, and then come back along path B. So we're going to consider another path called path C. Okay, and C is also reversible. So now we have a new path and a new cycle along path C, and C is also reversible. So we can say that, and it goes back along path B again. So this second cycle essentially follows C and then goes back down to B, okay, just to show you that it has the same path back. So if we look at this cycle, we can now write an equation in terms of the cyclic integral once again, and we can say that this is equal to 0 again because it's reversible. And now we have the integral from 1 to 2 of dq over t along path C now, plus the integral from 2 to 1 dq over t along path B once again. And we can call this equation 2. Now, once we have this, we can say if we subtract 2 from 1, so if we subtract just number 2 from number 1, we actually get the following equation. We get that the only way that these two equations can be satisfied is that the integral from 1 to 2 of dq over t for A is equal to the integral from 1 to 2 of dq over t for C. So what this states is, what this concludes is that since dq over t, or the integral of dq over t, is the same for all reversible paths between state 1 and state 2, it means that dq over t is independent of path. So we remember that if we have the same equation for from 1 to 2 of dq over t is equal to 1 to 2 of dq over t for path A and path C, then another path D would have exactly the same value. So it's not a function of the path, okay, such as work. Work is a function of the path. So we can say that dq over t is a function of only n states. So we only need to know state 1 and state 2, and we would find essentially the change in dq over t. Okay? And this change in dq over t is actually called entropy. So this property is called entropy. And what we can write is that ds, so the change in S is going to be our value for entropy, is equal to dq over t for a reversible process. Okay? And we can rewrite this equation if we want to as dq is equal to t ds. Okay? But the definition of the change in entropy is given by this equation right here, where S is equal to entropy. So if we have this equation, we can say that the change in entropy can be found by integrating the above equation. So we would have that, for example, the change in entropy between 0.1 and 0.2 above would be S2 minus S1 is equal to an integral from 1 to 2 of dq over t reversible. Okay, and we're going to keep reversible for now because we know that it's for dq over t reversible. We haven't proven it yet for an irreversible process. For now, it's all as if it was a reversible process. And in order to solve it, we need to figure out either we have a constant temperature and we can take the temperature out of the integral, or we need an analytical relation between Q and T. So we need to have Q in terms of T or T in terms of Q in order for us to solve the problem. Okay? Now the entropy, S, is equal to entropy, and the units of entropy are kilojoules per Kelvin. Okay? And the units for specific entropy is going to use a lowercase s. Okay, so sometimes it's going to be hard to determine the difference between the two, but in the lectures, I'll try and always say either specific entropy or lowercase or uppercase s. And this is equal to kilojoules per kilogram Kelvin. So just divided by kilograms, just as usual for specific entropy. Now, this integral that we just did is for a reversible path. But if we do the integral for a reversible path between 2 points, and the change in entropy is independent of the path, then that means that we can say, but once evaluated, so once we've evaluated this change in entropy, then we know delta S, or the change in entropy, for all processes between the two states. So in order to figure out the change in entropy between two states, we need to do an experiment with a reversible process. However, once we know this change in entropy, or we know the amount of entropy at a certain state, so let's say, for example, we have state 1, P1 is equal to 100 kilopascals, then P2 is equal to 1000 kilopascals, and we know that the temperature at 1 is 20 degrees Celsius, we know the temperature at 2 is 200 degrees Celsius. If we know the delta S between these two values, this delta S is always valid for any two systems between these two states, no matter if the process is reversible or not. So essentially, we can find values for S, we can tabulate the values for S, we can make a diagram with temperature versus S, for example, and from there, we can actually solve for any problem that is reversible or not. So it stems from a reversible experiment. However, since entropy is independent of path, it can actually be used for any process that you want. So it can be used for any process. So that's the conclusion from this. Now, what about the absolute value of entropy? So we've looked at the change in entropy, but we haven't looked at the absolute value of entropy. So the absolute value of entropy is defined as sort of an arbitrary point, an arbitrary place. And what we do is we say that the entropy of pure substances is 0 at absolute 0 temperature. So at absolute 0 temperature, S is equal to 0. But the value of S doesn't really matter in itself. What we're interested in is delta S. So we're always interested in the change in entropy of a system. We don't really care about the absolute value of entropy. So we're interested in delta S and not necessarily S. Okay? And this absolute value of entropy is actually sometimes also called the third law of thermodynamics. It's based on observation of low temperature chemical reactions, and there's an arbitrary reference state that we call S is equal to 0 when we have absolute 0 temperature. But we could have called S is equal to 1000 at absolute 0 temperature. The only interest we have is the change in entropy as opposed to just the entropy in itself. Now, just like our previous properties such as H, U, and volume, if we draw a TS diagram, so instead of a TV diagram, if we write a TS diagram, we have the same kind of system where we have a region here in the middle where we have a saturated mix where our S would be equal to 1 minus X times SF plus X SG. Okay, so in the same way as we had before, we can find our S from these values right here. And we usually use specific S, so we usually use our specific entropy, so divided by the mass. And in the same way as before, if we know pressure and temperature outside of the region, we can find S from tables. And if we have our S to the left here somewhere in a compressed liquid, we either know from our tables if we have a really high pressure, then you would know what to do. You would go to your table A6 for water, for example. But if not, you would A7 for water, sorry. But if not, you would use S is equal to SF at temperature. Okay, so it works in exactly the same way as the other properties, and it's mainly a function of temperature. Okay, so moving on from this, let's now look at entropy change in reversible processes. So let's look at an example of an entropy change in a reversible process. And the perfect example of a fully reversible system and with multiple processes is our Carnot cycle. So we can analyze our Carnot cycle now from the previous module and look at how it would be affected by the change in entropy, essentially. How can we measure the change in entropy of our Carnot cycle? And for now, entropy is just dq over t. We'll look at what it is a little bit later in part 2. We'll look at what entropy actually means in terms of the molecular level in part 2. But for now, I just want to develop the relationships to understand what entropy is mathematically, and then we'll look at it, what it means in actual value form. Okay, so Carnot cycle, what does it look like? Well, we remember if we have the PV diagram of our Carnot cycle, we remember we had 4 different points, point 1, point 2, point 3, point 4, and we had this cycle that went around, and we know in the cycle we had QH coming in, we have QL coming out, and we know that this line here is at TH, and we knew that this line here is at TL essentially. Okay, and we remember that from 1 to 2, we have an isothermal expansion. In our boiler. Then from 2 to 3, we have adiabatic expansion. In our turbine. Then from 3 to 4, we have isothermal compression. In our condenser, I'll call it C. And then from 4 back to 1, we have an adiabatic compression. And this is in our pump. And so we can look at the Carnot cycle and try to determine our change in entropy through our system throughout. And obviously this is a reversible process, so it's going to make things easier for us just by looking at it. So number 1, let's look at the first one. Let's look at the isothermal at TH. So we know that the process is isothermal at a temperature H. So for this, we can say that S2 minus S1, okay, the change in entropy is equal to the integral of dq over t from 1 to 2. And from this, we know that our temperature is constant. So we can take out from the integral our temperature. So you can see how this is actually useful because our temperature comes out of the integral. And so we're left with the integral from 1 to 2 of dq alone. And so we have that this is equal to q from 1 to 2 divided by th. So the q into our system is positive. So if our q into our system is positive, it means that S2 minus S1 is going to be positive, and it means that delta S increases. Okay, so we keep the same convention for Q. Q is in positive and out negative, so our delta S is going to be increasing. So we're increasing our entropy, okay, in process 1. In process 2, we have adiabatic, and what adiabatic means is dq is equal to 0. There's no change in heat. So if we look at our S2 minus S1 is equal to the integral of dq over t, if the change in q is equal to 0, then the integral of 0 is just going to be 0. So we have that S, and I should put S3 minus S2, sorry, because this is between 0.3 and 2. So S3 minus S2 is equal to 0. No change in entropy there. Then in part 3, we have S4 minus S3 is equal in the same way as before, but now with our TL, we have Q from 3 to 4 over TL. And this is a negative value because our Q is going out of our system. And so we have the delta S decreases. Okay, so our change in S decreases. And number 4 is going to be the same thing as number 2. It's also adiabatic, so we have that S1 minus S4 is equal to 0. So if there's no change in heat, if there's no heat transfer in our system, we're usually going to have a system that has no change in entropy. If there's no heat being transferred or nothing being transferred, we usually have no change in entropy. So we can say that entropy remains constant when a process is adiabatic and reversible. And if it's adiabatic and reversible, we also call it isentropic. Okay, an isentropic process is a process where the entropy does not change. So if we say something is isentropic, we usually assume that it's reversible, and it could also be adiabatic. Okay, so it's one where we don't have a change in entropy. So now, we've drawn our system on a PV diagram. We've drawn our Carnot cycle on a PV diagram. Sorry, I didn't put the V here. So now let's look at what it would look like on a TS diagram. So let's try and draw the cycle on a TS diagram. So we're going to use a TS diagram, which is just T versus S, okay? And I'm going to make the diagram a little bit bigger actually, just to make sure that we see it well. So we have our T and our S here, and we're going to draw the process. So the process starts with a certain amount of entropy. Let's call this entropy A, for example. Okay, so we'll start with an entropy A, and we know that at the start of our process we have a TH. At point 1 we have a TH. So we can draw point 1 being somewhere here. So we have 1 is our value here. Now, once we have process 1, we know we go from 1 to 2, and from 1 to 2 we're going to increase the entropy in our system. Okay, we know that S2 minus S1 is greater, so we know that we're going to get to a point B, for example, for our entropy, and we're going to do it at constant temperature. So we have 1, 2, 2, which should be located around here. And so we have a process from 1 to 2 that looks something like this. Just a flat line along TH from a small entropy to a larger entropy. Then our process from 2 to 3 is isentropic, so we have no change in entropy, and we go from 2 to 3. But we have a change in temperature, so now we go to TL. Then we have a process that goes from 3 to 4, which is going to be at constant temperature L. And finally, a process that goes back. So this is what our process would look like on a TS diagram. A very simple design. And we know that we can write our equations here. S2 minus S1 is equal to Q from 1 to 2 over TH. And S4 minus S3, the two changes in entropy essentially, is Q from 3 to 4 over TL. So if we rearrange this equation, we actually find that Q from 1 to 2, okay, and I'll write it to the right here. So Q from 1 to 2 is equal to S2 minus S1 times TH. Okay, so we know that Q from 1 to 2 is S2 minus S1 multiplied by TH. Now, if we look at our TS diagram, if we have the change in entropy and we have the temperature of the hot side that is constant, can we somehow figure out what our QH or our Q from 1 to 2 would be for our system? Well, Q from 1 to 2 can be also called QH. And if we look at the diagram, S2 minus S1 times TH is actually the area under the line 1 to 2. So I'm going to draw it in green. This area here, all the way down to the bottom, is going to be equal, this area is going to be equal to QH. So we can find QH from the diagram itself. Now, Q from 3 to 4, which can also be called QL, is equal to S4 minus S3 times TL. So the area under this curve, so under 3 to 4, in blue, is going to give us, our QL. So the area under the curve is going to give us our QL. So we can say that QH is equal to the area under line 1, 2, and QL is equal to the area under line 3, 4. So let me just write those so that we have them. So QL is equal to area under 3, 4, and QH is equal to area under 1, 2. The whole area under it. Okay? And we remember that for a cycle, we can also say that work net is equal to QH minus QL. So that means that if we have QH minus QL, the work net is actually equal to the area of QH minus area QL, and that in turn translates to, I'm going to draw it in white, and from top left to bottom right, the area in here would actually be equal to the work net. So we can find all of our values from a graphical representation of what is happening in our system. Okay, so it's pretty cool that from a TS diagram, if we know the change in entropy, we can find work, we can find QH, we can find QL, and we can go even further than that. So our work net is essentially we can also call it the area 1, 2, 3, 4. So it's just the area bound by the lines 1, 2 to 2 to 3, 3 to 4, 4 to 1. Okay, and we can go even further than this and say we can look at the thermal efficiency. Thermal efficiency is equal to work net over QH, or Qin, right? It's our QH is Qin. So we have that this is equal to area 1, 2, 3, 4 divided by the area under 1, 2. And this gives us another explanation of how we can increase efficiency. So the way to increase efficiency is to, for example, increase TH while TL remains constant, or bringing down TL in order for our TH to stay at the same level, and bringing down our TL, which means more work would be done as a proportion of QH. Okay, it's kind of the same thing as before. We were just looking at it from a different perspective, but in this perspective, you can also see how you can improve your efficiency just by looking at the graph and saying, okay, I need to make my work net bigger, and my QH has to be a smaller proportion of that work net, so we can change TH or TL to help us get a better efficiency, essentially. Okay, so the same thing can be done for a refrigerator. So the refrigerator process is just the exact opposite way, and so you would just have the same diagram but the opposite way, and you can do the same type of analysis for a refrigerator. Now, for a reversible process, we can say that the heat transfer to or from a system is shown as the area under the TS diagram. So let's write it just to have it. So for a reversible process, the heat transfer, so Q, to/from, so it can be to or from a system, is shown as the area under a TS diagram. So the area under the curve of a TS diagram would give us your heat, essentially. Okay, so let's say we have, for example, if we have a system, so let's look at an example of this statement. So let's say we have a TS diagram And in this TS diagram, we have our lines of superheated, compressed, and mixed. And we're told that we have a process happening from 1 to 2, okay, from 1 to 2 at constant temperature. Then we can say that in this case, point 1 and point 2 are at our SG. So this is our SG and this is our SF, right? We know that these are our values for S at the boundaries. So we can say that SG minus SF is equal to S2 minus S1, which is also equal to, and we're going to be using specific here. Okay, so we're going to use specific S's, so lowercase s's, is equal to 1 over mass times the integral from 1 to 2 of dq over t reversible. Okay, so we're using 1 over m because we're using specific, so we just divide the mass on the system. Now, we know in this case we have a constant pressure and constant temperature system, right? We're inside the region, the saturated mixed region. Our temperature is constant as shown here. So T is constant, but our pressure is also constant. Our pressure stays constant within the saturated mix. So we have that S2, and this is lowercase again, so just make sure that you write it as lowercase s. So S2 minus S1 is equal to 1 over m, and now we can take our temperature out of the bracket because we know that temperature is constant, times 1 over T, integral from 1 to 2 of dq reversible. And so we're left with the fact that S2 minus S1 is equal to Q from 1 to 2 over mass times temperature. And we can also rewrite this as the following. So if we have lowercase s2 minus s1, we can say that this is equal to Q from 1 to 2 over m times 1 over t. And we can rewrite this value here as little q, okay, or specific heat, essentially, okay, heat divided by mass. Now, let's assume that this is a constant mass system. So it's a piston cylinder system, for example. If we have a constant mass system and we apply the first law, we are going to have that Q in minus work out is equal to delta U divided by mass. Okay, so I'm already bringing the mass over to the other side. If not, it would be, the mass would be on the left and you would have Q uppercase, but I'm using the lowercase version of this, plus delta KE over mass plus delta P over mass, and these two go to 0, assuming we have a simple system. And we're left with little q in is equal to U2 minus U1, okay, specific internal energy 2 minus specific energy internal energy 1, and plus our work boundary, but our work boundary is lowercase. Okay, and this work boundary is going to be equal to U2 minus U1 plus P2 V2 minus P1 V1. Okay, and if we look at this process here, we see that for a constant pressure process, so for constant pressure, we would have, this is equal to, so if we combine these terms together and we combine these terms together, we would have H2 minus H1. So essentially what we came out with is that Q is equal to H2 minus H1 in this case, which means that the entropy, S2 minus S1, or the specific entropy, okay, lowercase, is equal to H2 minus H1 over temperature. And in the case of our example, we can say that Sg minus SF, and I'm just checking, yes, so Sg minus SF is equal to Hg minus HF over T. So we now have a relation between these two values and between these values of S and H. So in our tables, this is how they calculate our thermodynamic tables for SFG. So for Sg minus SF, what they do is, remember that Sg minus SF is also called SFG. The SFG is calculated from your Hg minus HF over that specific temperature you're at in the table. So if you go to table A4, you can actually check and the number would come out right. So that concludes the first part of Module 6. In the second part of Module 6, we're going to define entropy in terms of what it means in a molecular way, and then we're going to look at important relations that we can use to sort of solve problems using entropy and look at some examples. So we'll see you in part 2.